solving this problem called bracket sequences 1. So our task is to calculate the number of valid bracket sequences of length n. For example, when n equals 6, there are 5 valid sequences, namely these. So the only input is an integer n up to a million, and for that input we need to output the number of valid bracket sequences modulo 8,000,007. So let's head to the drawing board and see how we can solve this problem. So to get started, let's enumerate the valid bracket sequences for the values of n. So we start with n equals 1. So we will have a sequence of length 1. It can be either this or this. And none of these is valid. So for n equals 1, we have 0. And for n equals 2, so the first character can be either open and or closed, and the same goes for the second character. So we will have 4 possible bracket sequences. So either this and this, or this and this, or this and this, or this and this. And out of all these, only this one is valid. So there is only one valid bracket sequence of length 2. Now moving on to n equals 3. So we will have 8 possibilities here. So either this, 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 or this, 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 and so on. And as you can see, none of these will be valid because the length of this sequence is odd. So our first observation is that if n is odd, then there are 0 valid bracket sequence. And I hope this makes sense because for each opening bracket we need a closing bracket, and this tells us that the number of character will be even. And since n is odd in this case, this means that we won't have any valid bracket sequence. Now we will move on to n equals 4. And in this case, you can check that there are 2 valid sequences, which are these 2. And we can see that these would be the unique sequences by the following logic. So we know that the first character has to be an opening bracket, which means that this opening bracket needs a matching closing bracket, and it can be either one of these 3 characters. So in the first case, if we choose this to be the closing bracket for this, then we have this arrangement. And in the second case, which would be choosing this to be the closing bracket for this, we would have a problem here because we will have this character by itself in the middle of these 2. So that can't work. And finally, the third case is when this is the closing bracket for this opening bracket. And in the middle, we can put any bracket sequence of length 2, and there is only one such sequence. So the final answer for when n equals 4 is 2. So far we have this remark, and we also have an obvious fact, that is the number of opening brackets equals the number of closing brackets. And this is self-explanatory because for each opening bracket we need a matching closing bracket. And now let's see if these 2 conditions are enough. So if a sequence satisfies these 2 conditions, would it be valid automatically? So this first condition tells us that n has to be even, and this second condition tells us that the number of opening brackets should be equal to the number of closing brackets. So this sequence is of length 6, which is even, and it has 3 closing brackets and 3 opening brackets. However, it is not valid because one of the criteria for a valid bracket sequence is that the number of opening brackets is always greater than or equal to the number of closing brackets in any given prefix. But here in this prefix, we have one closing bracket and 0 opening brackets. So the number of opening brackets here is not larger than the number of closing brackets, which makes this sequence invalid. And this gives us our third condition for a valid bracket sequence, which is that the number of opening brackets is always greater than or equal than the number of closing brackets in any prefix of our string. So if you consider this valid bracket sequence, you can see that in any prefix, the number of opening brackets is larger than the number of closing brackets. So given these three conditions, how can we enumerate the number of valid bracket sequences? One interesting thing we can see here is that we actually know the number of sequences that satisfy only these two first conditions. So the number of sequences that are of length n, where n is even, and where the number of opening brackets is equal to the number of closing brackets, can be easily calculated using the binomial coefficients. So we will have a string of length n, where n is even, so this n can be represented as 2 times some integer k, and this string will contain k opening brackets and k closing brackets. So the total number of sequences that satisfy the first two conditions would be equal to the binomial coefficient of 2k choose k. And each valid sequence is just a choice of the k positions for the opening brackets. So here k is equal to 3. So making a sequence here is simply choosing the positions for the opening brackets. So if I choose to put opening brackets here, here, and here, then automatically the other positions will contain the closing brackets. And in this example here, we chose these positions for the opening brackets, and automatically the other positions were taken by the closing brackets. So the number of sequences that are of even length, and their length would be equal to 2 times k, and where the number of opening brackets is equal to the number of closing brackets, i.e. we will have k opening brackets and k closing brackets, will be just equal to the binomial coefficients of 2k choose k, and this also can be written as c choose k from 2k, and this will actually represent all the sequences that satisfy these two conditions. However, this does not account for this third condition. So all we know so far is that our answer will be less than or equal to the binomial coefficient of 2k choose k. Namely, 2k choose k counts all the sequences, including those where the number of opening brackets is less than the number of closing brackets in a given prefix. So our answer should be equal to 2k choose k minus the number of sequences that do not satisfy the third condition. So the question we have to answer now is the number of such sequences. So what is the number of sequences that do not satisfy the third condition? To answer that question, let's consider an invalid sequence, one where the number of closing brackets is greater than the number of opening brackets in a prefix. For example, something like this. So this is a sequence of length 4, and as you can see, in this prefix, we have one opening bracket and two closing brackets. So this is not good. And to be more explicit, let's actually list all the sequences of length 4 that have two opening brackets and two closing brackets. So how many such sequences exist? As we said, we will have 4 positions, and for those 4 positions, we will choose 2 positions for the opening brackets, let's say. Then this will be equal to 6. That is to say, we will have 6 such sequences, and they will be the following. So these are the 6 sequences that have 2 opening brackets and 2 closing brackets. So this one is valid. This one is also valid. However, this one is not valid. And so isn't this one, nor this one, nor this one. So all of these are invalid because in this prefix we have 2 closing brackets and 1 opening bracket. In this prefix here we have 1 closing bracket and 0 opening brackets. The same goes for this prefix and for this prefix. So our goal here is to count the number of these sequences, and in order to do that, I will actually perform a mapping in the following manner. So for each one of these sequences, I will locate the first position where this sequence becomes invalid. For the first sequence, this is the position where this sequence becomes invalid. And what I will do is that for the remaining of the sequence, I will just flip each opening bracket to a closing one and vice versa. So this becomes open, close, close. This was open, so I will have to switch it to close. So I'll do the same thing for the remaining sequences. So here this is the first position where the sequence becomes invalid. So for all these remaining characters, I will flip them. So this becomes close, 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 open. The same goes for this sequence as well. It became invalid from here. So it will give me close, close, open, close. And finally for this it became invalid also at the first position. So this becomes close, open, close, close. So what you can notice here is that each one of these resulting strings contain one opening bracket and 3 closing brackets. And in general, if we started with k opening brackets and k closing brackets, then the newly generated strings will contain k minus 1 opening brackets and k plus 1 closing brackets. Not only this, but we actually generated all strings that contain one opening brackets and 3 closing brackets. So basically this is equal to 4, choose 1. Basically we are choosing one position for the opening bracket. So it can be either in the first character, or in the second character, or in the third character, or in the fourth character. So what we notice from this is that there is a bijection between the number of sequences that do not satisfy the third condition and the number of sequences that contain k minus 1 opening brackets and k plus 1 closing brackets. And from combinatorics, we know that that would be equal to 2k, choose k minus 1. And to illustrate this better, let's consider another example. For example, if n is equal to 6, we would consider the following invalid sequence. So let's say we have 2 opening brackets followed by 3 closing brackets and finally 1 opening bracket. So up till here the sequence is still valid. We have 2 opening brackets and 2 closing brackets in the prefix. So it won't become invalid until we reach this position. So we will just switch the symbols in the remaining of the sequence to get the following. So we have open, open, close, 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 and finally we will switch this open to close. And in this resulting sequence, we will have 2 opening brackets and 4 closing brackets. Since we started with k equals 3, it makes sense that we will get k minus 1, which is 2 opening bracket, and k plus 1, which is 4 closing brackets. And you can check for yourself that there is a bijection between these two. So this will give us our final answer. Now that we have all the parts of our puzzle, so we knew that answer would be equal to 2k choose k minus the number of sequences that do not satisfy the third condition, and we just figured out that this is equal to 2k choose k minus 1. So our answer will be just the difference of these two. So our answer will be just equal to 2k choose k minus 2k choose k minus 1. So we can just stop at this and see how we calculated binomial coefficients in previous problems, and just compute this and calculate the difference and we will be all set. But we can simplify this further. So this would be equal to 2k factorial divided by k factorial times k factorial minus 2k factorial divided by k minus 1 factorial times k plus 1 factorial. And in order to have a common factor between the two terms, we see that the numerator is identical in both terms, but we see here that we have a k factorial, whereas here we only have a k minus 1 factorial. So in order to make this equals to this, we have to multiply this by k. So we can multiply the numerator and the denominator by k. And additionally, we see here that we have k plus 1 factorial, whereas here we only have k factorial. So we can pull an extra k plus 1 outside. So this becomes 2k factorial, the first term does not change, divided by k factorial times k factorial, minus, we will have an extra k here in the numerator, so we can just bring it out. And as we said, we're gonna bring out k plus 1 from the numerator, so we'll have k divided by k plus 1 times 2k factorial divided by k times k minus 1 factorial will be just k factorial times, as we said, bringing out a k plus 1 from this will only give us k factorial. So we see that we got a common factor between these two terms. So we can simplify by factoring this from both terms and getting. So here we'll only be left with 1 minus k divided by k plus 1 times 2k factorial divided by k factorial times k factorial. And this simplifies too, so the common denominator here will be k plus 1, and we will get k plus 1 minus k, which will give us 1 divided by k plus 1 times, and this is just the binomial coefficient of 2k choose k. So our final answer will be just 1 divided by k plus 1 times 2k choose k. So we can write that our answer in terms of k will be equal to 1 over k plus 1 times 2k choose k. And remember that this k relates to the n from the input in the following manner, namely k is equal to n over 2. And this division will be valid because we made sure that n was even. So we can just stop here and calculate our answer using this formula. And it is worth mentioning that what we just calculated is known under the name of Catalan numbers. And these are very famous numbers in combinatorics. So let's check out the Wikipedia page about them. So the Catalan numbers form a sequence of natural numbers that occur in various counting problems, often involving recursively defined objects. They are named after the Belgian mathematician Eugène Charles Catalan. And as we found, the nth Catalan number is given directly in terms of binomial coefficients by the following formula. So that's precisely what we got there. And these are the first few terms of the Catalan numbers. And you can check out here all the things that the Catalan numbers actually enumerate, and there are a bunch of them. So this is the example we worked out. Cn counts the number of expressions containing n pairs of parentheses which are correctly matched. And there is a bunch of other applications that I invite you to check out. And finally, before moving on to the code, I will actually work out a formula that does not involve binomial coefficients. So here, I will just abbreviate this as CK. So we found out that CK is equal to 1 over K plus 1 times 2K choose K. And by the same definition, I know that Ck minus 1 is equal to 1 over k times the binomial coefficient of 2 k minus 1 choose k minus 1. So if I compute the fraction ck over ck minus 1, I will get 1 over k plus 1 times 2k choose k divided by 1 over k times 2 times k minus 1 choose k minus 1. So this would actually be equal to k divided by k plus 1 times 2k choose k divided by 2 times k minus 1 choose k minus 1. And this is equal to k divided by k plus 1 times 2k factorial divided by k factorial times k factorial divided by 2 times k minus 1 factorial divided by k minus 1 factorial times k minus 1 factorial. So if I rearrange this, I will get k times k plus 1 from this first term times, I will bring this to the numerator and I will flip it. So I'll get 2k factorial divided by k factorial times k factorial times k minus 1 factorial times k minus 1 factorial divided by 2 times k minus 1 factorial. So this will be equal to k divided by k plus 1 times, I can simplify this with this and I will only be left with a k, and I can do the same here, so I will be left with a k here again. So in this term I'll get 2k factorial divided by k squared times 1 over, and I will just expand this, so this will be 2k minus 2 factorial. So I can simplify a k here and here, so I'll get 1 over k times k plus 1, this k plus 1 from here and this k from here, times 2k factorial, which would be equal to 2k times 2k minus 1 times 2k minus 2 factorial divided by 2k minus 2 factorial. Basically, I just wrote down the first terms of these 2k factorial, and I can get rid of this, and I can also simplify a k from here and from here, so I'll get 4k, minus 2 divided by k plus 1, and what I started with was ck divided by ck minus 1. So I got a recurrence relation for ck, namely ck is equal to 4k minus 2 divided by k plus 1 times ck minus 1. And all what I need is an initial condition, namely C0, and this would represent just the empty string, which would be equal to 1, or we can also use C of 1, which will be just 1 as well. So if we have only one opening bracket, then as we saw, there is only one valid sequence, namely this one. So that's pretty much it. We got ourselves a recurrence relation. The only drawback with this is that we have this division right here, but we can remedy it by using binary exponentiation to find the modular inverse for this. And we will just raise this to mod minus 2 as we saw in previous problems. And we will just compute the answer in linear time plus whatever complexity we require to calculate the modular inverse each time. So let's check out our code. So this is our program. As we said, we're gonna require the modular binary exponentiation function that we saw in previous problems in order to compute the modular inverse. And we will start by reading n. Then we will check if n is odd, because as we saw in the initial condition, if n is odd, then there are 0 valid bracket sequences. So if that's the case, we will just output 0 and return. Otherwise, we will divide n by 2, because as you saw, we calculated the answer in terms of k, which is in fact n divided by 2. So after we make sure that n is even, we will just divide n by 2, and we will declare this vector that will help us store the valid bracket sequences for all values from 0 up to n included. And we will set the initial value for the number of valid bracket sequences for 0 to be equal to 1. Then we will calculate the other values recursively. So for each I, we will calculate the number of valid bracket sequences with I opening brackets as being equal to 4 times I minus 2. Precisely what we got here. So we got 4k minus 2 divided by k plus 1. So since we cannot divide when we are computing an answer modulo a prime number, we have to multiply by the modular inverse. So we multiply here by the modular inverse of I plus 1, and we calculate it by using the modular binary exponentiation of I plus 1 raised to the mod minus 2. Afterwards, we will just multiply whatever we got by the valid bracket sequences with I minus 1 opening brackets. And at the end, we will just output our answer that will be stored at position n in our array. So that's pretty much it. Let's go ahead and submit. So that worked. Thank you very much for watching. See you in the next video. Bye bye.